Hello, I'm Zoe Turner, and this is my lab 4 on Faraday's Law. The purpose of this lab is to collect observational data for a magnet falling through a conductive tube of aluminum foil. We make a model of the magnet and tube, and we compare the computational predictions with my observed data. The principles we use in this is magnetic flux to measure the total magnetic field, Faraday's law, the magnitude of EMF is proportional to the rate of change in time of the magnetic flux in a current, and Lenz's law, the induced electric current flows in a direction that is such that the current opposes the change in the that induced it. Our physical model, we use the magnetic force, which is force times length times LD or DL times magnetic, and we find B using the Biot-Savart law. We use Lenz's law, and we found that the current flows counterclockwise and the magnetic field points upwards. The falling magnet, and as the magnet falls, it creates changing magnetic field at the ring, and the deflux points downwards. The equipment we use is a bar magnet, smartphone, foil, which is 0.3 meters in length, 0.005 meters in width, and 0.025 meters in the inner radius, and the outer radius is 0.03. And it has a resistivity of 2.65 e to the -8th. And we also need a meter stick. In our procedure, we note the properties of the foil and the bar magnet. Then we mark the end pole on the magnet. After that, we drop the magnet through the top of the foil opening and measure the time that it takes to get to the floor. In our observation, the experiment, it was averaged about 1.41 seconds in our 5 different trials. In my computational model, it was 0.42 seconds. The magnet that falls in the aluminum tube than in free space, it falls faster or slower than in free space, and the downward force of less magnitude. Here's my simulation. You can see in the code, I calculated the gravitational force on the magnet, and I used the magnetic force from the tube on the magnet. And on the other side, I calculate the magnetic force on the magnet, and I calculate the net force. Oh, here's some more. This is what I did for calculate the deflux of each ring due to the falling magnet, and you can see in the graph and the little magnet thing where it says F mag is pointing upwards, but F gravity is much stronger than F magnetic. So what ifs and sources of error. Some errors may come from our reaction time or recording the physical times of the magnet falling onto the table, which is reasonable because humans' reaction times are much shorter than if a computer were to do it. So what if the resistivity of the conductor was reduced to as close as 0 as possible? How would the dynamics of the falling magnet change? I think if the resistivity was at 0, I believe it would be like infinitely fast. It would just fall straight through. Like what we would see in a second, it would happen almost instantly. So what if holes or slots were cut into the tube? How would this affect the ring currents in my model? If there were holes in the tube, this would affect the ring currents. It would, depending on where the holes are, it could create some inconsistencies in the end calculation of our deflux, because there would be other forces, in quotes, acting onto it. Like there would be more air resistance because more air is allowed to flow into it. And yeah, thank you for watching my video. Stay tuned for the next lab.